So, as John said, I'm Phil Hughes from the University of Manchester. I haven't actually travelled far this morning. I live in Penarth, but still, let's pretend I've come all this way. So I'm going to talk about the glacial history of the Mediterranean mountains in the Quaternary. So that's from right now to the last ice age and beyond. Okay. A lot of the information, plug a book here, this is probably a few years ago now, in the Geological Society special publications, and that's a compilation of work. Today I'll be presenting mostly my research, but there's lots of other people working in the Mediterranean, and this book summarises the work done from Turkey through to Morocco and Spain by various authors. Okay, that photo, by the way, is Montenegro, the mountains of Montenegro, and we'll be visiting there on our tour. So what about glaciers today in the Mediterranean? Now, glaciers are not commonly associated with the Mediterranean mountains, and this map illustrates where we've got modern glaciers, so glaciers dynamically moving ice bodies, so they rotate and move mass through the glacier. That's what defines a glacier, but also permanent ice patches. So these are static patches of ice, okay, and perennial snow in the Mediterranean mountains, and this is where we find them. And this is the list here. We go through Morocco, we'll visit later. It doesn't have any modern glaciers today, but it does have some permanent snow patches and permanent ice patches. Sierra Nevada used to have glaciers up until the 1930s, but they've disappeared now, become buried by debris. The nearest real ones, if you like, on the west here are in the Pyrenees. There's several tens of small cirque glaciers in the mountains of the Pyrenees. The Picos de Europa has some permanent ice patches. Used to be glaciers in several decades ago, but it's a common theme around the Mediterranean. What were glaciers 100 years ago, especially in the 19th century, end of the Little Ice Age, when climate was 1 degree cooler across, especially Northwest Europe, including here, the glaciers were much more common in the Mediterranean mountains, okay? Then we've got the Alpes Maritimes, very small glaciers. The number 6 is just east of Rome in the Apennines. The Calderone Glacier claims to be the southernmost real glacier in Europe, or used to be claimed until the Bulgarians got in on the act. I'll tell you about that in a minute. Then we've got several in the Balkans. Greece doesn't have any modern glaciers. People argue about whether there were any in the Holocene. But the southernmost glacier in Europe today is claimed by, in the Pirin and Rila, which is by, it's called the SWGA Glacier, okay? And then we go to Turkey, and there's lots of glaciers in the far east of Turkey. The biggest glaciers in, if you call that the Mediterranean, actually drains in that way to the Persian Gulf. These are the biggest glaciers on that map. Quite tricky to work in that area, of course. It's on the border with Iran and Iraq. Okay, so that's the current state of ice today. And this is some photos. There's the mountains in the far east of Turkey on Mount Silo, big valley glaciers. They're not that big, but for someone who works in the Mediterranean, that's quite big, okay? Whereas we're talking about small features like this. They're in niche topoclimatic settings. They're fed by avalanching snow. They're heavily shaded. And in theory, for glaciologists, glaciers shouldn't exist. Glaciers are very closely related to climate. What comes in through snow is offset by what's melted by summer temperatures. And in most of the places on that map, glaciers theoretically shouldn't exist at the altitudes we find them, but we do find them, breaking the laws of physics, because we get snow accumulation several times that falls through the sky, and that happens because of avalanching snow and wind-blown snow. Okay, some of the bigger glaciers, the biggest like this one on Mount Silo, is more in line with climate. The bigger the glaciers get, the more they have to align with the equilibrium of the regional climate. But in niche topoclimatic settings, they're often several hundred meters below the theoretical snow line, if you like, for where glaciers should exist. Global climatic context, we're not just going to be talking about the modern, I'll be going into the ice ages and understanding why glaciers existed in the past, in the ice ages, of the Quaternary and what it means for climate. This is the oxygen isotope record, so effectively less ice at the peaks, the interglacials. It's the interglacial we're in today at the Holocene, and that's the height of the last ice age. Okay, so we've got multiple ice age cycles, glacial cycles, and in the Mediterranean record, we've got evidence of glaciations from this ice age here, here, and here, but we don't have evidence from these. That doesn't mean there would have been ice glaciers in all these ice ages, all these glacial cycles. It's just that these were smaller than this one, so the evidence is obliterated. Okay, the fact that we have glaciers, interglacials, like we're in today, is why I say there would have been glaciers all the time. Apart from the last interglacial, which we think was about 1 or 2 degrees warmer than today. But the point is, if we find glaciers in the mountains of the Mediterranean today, then the average conditions for the last 2 million plus years would have been glaciers in the mountains of the Mediterranean, often much larger than we see in the short interglacials. Okay, and that's the last glacial maximum height of the last ice age, about 25,000 years ago. Okay. This is a snowline map and a map of where the glaciers were in the last ice age, the Würm ice age, Swiss, Helvetica. And this is what we think the distribution was and the snow lines. It's hard to see exactly the snow lines here, but effectively what we're saying is as we go towards northwest Spain, the snow lines became much lower. In the Balkans, you can see around here, the snow lines, equilibrium line altitudes were down to about 1300. Now, this map pretty much maps on to the current precipitation patterns in the Mediterranean that we see today. So if you get your school atlas out, you'll see it's wettest in northwest Spain and also in the Western Balkans. And the fact that the glaciers were the lowest in these areas during the Pleistocene glacials, especially the last ice age, suggests that precipitation patterns were the same, not the values, but the patterns were the same as we see today. And that illustrates the importance of westerly systems from the Atlantic. Okay. And of course, you can see the Alps was covered by a much larger ice sheet contiguous across the mountains. Now, Bruno Messerli did this map. He did a publication in 1967. He started in Sierra Nevada with his wife, and they went round the Mediterranean in their VW camper van, observing the moraines and so on. And then he went all the way right and round and finished in the Atlas Mountains on Mount Toubkal, which I'll provide some information on. And he observed the evidence for the past glacial limits in the mountains of the Mediterranean. Seems fantastic. Okay, and we followed that up over the last few decades. Jamie Woodward and I wrote this edited volume. Jamie's at Manchester with me, and we mapped the current state of knowledge about the maximum extent of Pleistocene glaciers in the Mediterranean. And the map's pretty similar to what Bruno wrote in the 1960s, okay? The difference is these snow lines, Bruno suggested it was the last ice age, the last glacial maximum 25,000 years ago. But what we now know is it's much more complicated than that, and it's diachronous, this snow line. Some of the glaciers were at their largest 450,000 years ago. Some reached their maximum 25,000 years ago. So it was a bit simplistic to assume this is the snow line at the last glacial maximum. Okay, again, you can see more clearly now, this is a snowline map in the Pleistocene at the maximum extent of glaciers, which occurred at different times, but it matches the current precipitation distribution in the Mediterranean. Okay. So what we're talking about is the influence of depressions from the Atlantic and also generated in the Mediterranean itself, illustrating the altitude of the different ice masses. And again, we've got different sizes. The black colouring here is the extent, the cartoon, if you like, where the ice was, mostly over the Alps. There's a few subtle differences now. For example, we think over Dalmatia, we had significant ice cover going down to sea level with moraines on the beach. The Atlas Mountains had much more. And even in places like the Lebanon, there were mount glaciers, and there's very clear moraines in the Jebel Liban and also on Mount Hermon on the border with Israel. Okay. So what we're going to do is we're going to have a little tour of a selection of these places. I started my work in Greece in the Pindus Mountains when I had my PhD. Then I went on after Cambridge going to Manchester to work in the Balkans. Originally, I was supposed to be working in the Balkans, but it was at the time of the Kosovo troubles, and there was issues with NATO and Serbia and Belgrade and so on. It's always a theme, isn't it, these troubles? So I started my PhD in Greece. My supervisor at the time, talking about, just said to me, just be brave. That was before risk assessments were fully integrated. And then I went in 2004, 5 to the Balkans, interesting about the Balkans, you'll see in a minute, is that's really where the action was in terms of in Montenegro, Bosnia and so on. The glaciers, they were much, much bigger in the Pleistocene than they were in Greece. Also have a look at northwest Spain. We won't linger there too long. And then we'll finish off in the Atlas Mountains and look at the evidence we've got for the past glaciations. Okay, so the Balkans. So I started my PhD in northwest Greece on Mount Tymphy. Then I went on to Montenegro, Bosnia, and recently also worked on the Peloponnese. And what we're interested in doing is understanding differences in the altitude of the paleoglaciers, and what does that mean for precipitation distribution and atmospheric circulation through the Mediterranean region. So this is Pleistocene glacier maximum snowlines in Greece. So what sort of mountains do you need to climb in order to see the moraines, cirques, and features like you see in Wales, Scotland, and so on? Well, in the west, the lowest altitude glacial deposits and landforms, with ELAs around 1,600 metres in the mountains of northwest Greece. The mountains there reach about 2,500, 2,600 metres, and the snow lines, the equilibrium line altitude glaciers, was about 600 metres. So that means the glaciers were quite big. That's the midpoint of the glaciers. So glaciers went below that altitude, down to about 800 metres. As you can see, the moraines cut through here in northwest Greece. And that's where I started doing my PhD. And then you see a strong contrast with higher as you go further east. And that's simply a precipitation effect with drier conditions in the lee of the Pindus. Okay. So this is Mount Tymphy from a plane. This is the plateau. And what we're talking about here is not small glaciers, but big ice caps which completely submerged the landscape, and you get abraded, ice molded, ice scoured landscapes on these limestone plateaus. Mount Tymphy's limestone. Many of the places I've worked in, especially in the Balkans, have been on limestone terrains, and it produces a particular type of glacial geomorphology, glacier karst terrain. Okay. S and T, Scamnelli and Sapelabon villages where we've got end moraines, and so that glaciers completely submerged the mountain plateau and had outlet glaciers in the various valleys. And also this is the Vikos Canyon, which is the deepest canyon in Greece. And that would have been a conduit for glacial meltwater during multiple ice ages. Okay. So that's the sort of scale of ice we're talking about. This is the marine isotope stages. That's the last glacial cycle. That's the penultimate glacial cycle, and that's several back, okay? 25,000 years ago, 150,000 years ago, and 450,000 years ago. And what's important here is that the older glaciations, not the last ice age, but several ice ages back, were much bigger in Greece, whereas the last glacial cycle, the last glacial maximum, glaciers were quite restricted. They were restricted to the cirques here. And that was quite a big change of thinking, because as you remember, Bruno Messerli in his snowline map assumed the lowest and biggest glaciers in many places, like Greece, belong to the last glacial maximum. So this is the Tymphian, and that's not true. We now know they're much older, and it's much more complex in terms of the timing of the different glaciations. Now, let's just go back to this slide. We dated these features using uranium series dating. So they're in limestone terrain. Water percolates through these moraines. It dissolves the calcium carbonate matrix, and in between the boulder clasts, it then forms mini speleothems, if you like. So you get secondary carbonate cementation of these moraines, and we were taking the cements and applying uranium series dating to tell us the age of the secondary precipitate formation. It wasn't dating the moraine per se, but it was dating the secondary carbonate precipitation. But of course, the moraine has to predate that because it's the host moraine. So what we found is these moraines came at the limit of uranium series dating, greater than 350,000 years. There were clean carbonates as well, so there's no issues with the dating. And we found that in multiple valleys. So these older moraines, or the lowest moraines, appear to be very, very old. They also have well-developed soils on them, indicating they've been sitting there for a long period of time. And that was the big change in the early work, where we had this sequence. So we knew these smaller glaciers formed during the last ice age, but even then we didn't know exactly when that occurred. The last glacial cycle from 11,700 years ago, beginning of the Holocene, right the way back to 110,000 years ago. There's a 100,000 year window there. And we knew these glaciers in the higher search belonged to the last ice age, but we didn't know when exactly they were at their maximum. So for that, we applied chlorine-36 dating, and that's in this paper, PhD student James Allard, where we dated the surfaces of these boulders. How does it work? Well, effectively, a boulder like this, as soon as it's plonked there, it's exposed to the atmosphere, and you get cosmic rays, not just cosmic rays, but you get radiation from outer space, and we get, in the upper atmosphere, we get a stream of protons, lose an electron, then we get neutron flux to the rock surface. So what happens is these neutrons penetrate 2 to 3 meters through the rock surface, and it alters the geochemistry of the rock. And what we have is calcium is the target element, and that breaks down as it's bombarded by these neutrons through time to produce terrestrial cosmogenic nuclides, chlorine-36. So when that boulder was put there and not exposed to the atmosphere, it didn't have any chlorine-36 in it. The longer it sits there, the longer it's bombarded, then it will build up chlorine-36. So it's like a cosmic clock, if you like, and it tells us about how long surfaces have been exposed. It's not quite as easy as it may sound, though, because it relies on that surface being intact, staying there, not disturbed, and so on. A big problem with cosmogenic nuclides on Earth is erosion. So if you have an old moraine that may have been buried once, the matrix has been eroded, and the date you'll get will be the age it was exhumed and revealed to the atmosphere. It can topple if it's not from the last ice age, or even if it is from the last ice age. Periglacial activity, lots going on in the landscape. Boulders can topple at various times, so you're simply dating the time it toppled. But if you date enough samples and you're confident about their stability, then you can get sensible exposure ages. Okay. Another problem with limestone is dissolution of the rock surface itself. Cosmogenic nuclides after you go deeper than 5 centimeters into rock, the cosmogenic nucleus tails off dramatically, even though it can penetrate down 2 to 3 meters. So we're only really interested in the top 5 centimeters. If you've had dissolution of several centimeters in a limestone, then that causes all kinds of problems. So the best rocks for dating are really hard rocks, which surface which hasn't moved at all since the time the glacier retreated. Nevertheless, we got some interesting ages, and there was the general story was that the oldest moraines, or the largest moraines of the last ice age, dated to about 25 to 50,000 years ago. Or to be precise, 25.7 to 29.0, just before the last glacial maximum. Why not exactly at the last glacial maximum? It's because on Earth, we think that as we went to the last glacial maximum, sheets over North America and Scandinavia reached the maximum. But it was dry, the atmosphere was drier, and in the mid-latitude mountains like Greece, glaciers then retreated at the coldest part of the last ice age and reached their maximum earlier when there was moisture available to deliver the snow in the winters. Okay, that's what they look like. This is the modelling. How big are they? A few kilometres long. This is the older moraines belonging to the middle Pleistocene, but that's the state of Greece in the mountains, northwest Greece, around 25 to 30,000 years ago. And it's really important part of the work, not just for geologists, but also for the archaeologists, because there were modern anatomical humans coming through the Balkans at the end of the last ice age at around 20,000 years ago. So just after these glaciers reached their maximum, modern anatomical humans, we've got remains in the rock shelters in this mountain massif, several places. So this would have been the landscape that modern anatomical humans would have been dealing with when they migrated through southern Europe at the end or at the height of the last ice age. Mount Kelmos, this is an interesting mountain in southern Greece. This is the Peloponnese. Now, the Peloponnese are interesting because it's the southern tip of the Balkans, and we want to understand, well, first of all, were there any glaciers there? And if they were there, why were they there? What did it mean for temperature and precipitation? And on Mount Kelmos, it's quite interesting because we were expecting small glaciers. You go further south, I think it gets hotter. Even if precipitation stays the same, the snow line should raise. But what we found here is that the mountains covered the landscape, the ice caps covered the mountainous landscape, and this was completely submerged with ice, forming outlet glaciers. And this is in the southernmost part of Greece. There's also similar glacial features on the Taygetos, which are on the peninsulas of the very far south. Okay, and that's what it would have looked like. Okay, we're not talking, it's not Greenland, but still, it's significant ice, several kilometres long, submerging the central part of Mount Kelmos. And as I mentioned, on the Taygetos, to the south here, there would have been glaciers too. And even on Crete, we think there's significant ice masses on Crete, but it's not controversial so much. It's more people haven't really written much conclusively about the glacial extent on places like Crete. So there's still lots to do in the Mediterranean mountains. This is how it looks. The good thing about my work, I'm a soft rock geologist, as it were. You can see it at the surface. So it's easy for me just to wander the landscape and see the geology. I don't have to deal with sections and so on. So you have the outlet glacier at the top here. Then you have big alluvial fans, and you have these cemented benches. And again, we've dated them with uranium series dating. And the old glaciations date from the Middle Pleistocene, same as in northwest Greece. Okay. We also apply optically stimulated luminescence, which dates sand, burial of sand, how long it's been buried. And these come out for the alluvial fan of big aggradational phases 150 to 450,000 years ago. Again, that's consistent with big ice caps over the mountains in the Middle Pleistocene, and again with the uranium series. That's the sort of sediment build-up we're dealing with. So we've got ice caps, imagine, in the mountains, eroding the landscape and producing huge thicknesses of fluvial sediment downstream. And this is tens of meters thick. And again, we've been able to date it using those techniques. Then we've applied for the most recent glacial deposits, this technique I mentioned before, chlorine-36. So this, you take a little bit of rock off the surface. We're assuming that boulder's been sitting there ever since the ice retreated. We see how much chlorine-36 has built up in the rock, and that's the cosmic clock, if you like, tells us how long it's been exposed. And these come out a little bit earlier than in northern Greece, where I said it was between 25 and 30,000 years ago. These have ages which are 30 to 40,000 years ago. But again, the lesson here is that the glaciers of the last ice age reached their maximum, not at the global last glacial maximum, because of the global last glacial maximum, we had the biggest ice sheets over North America, Scandinavia, and even Britain. It was too dry in the Mediterranean. So remember, we get glaciers in the Mediterranean today. So if we can get them today, what do we need to reach their perfect sort of climate, if you like? Well, it's precipitation is the real important factor here. Of course, it needs to be cold, but the point is we want it to be cold and also wet. And that occurred earlier in glacial cycles. And as we get towards the coldest part of ice ages, the glaciers are starved of moisture, abandon the moraines. And then as we go to 25,000 years ago, the glaciers had gone up valley. Okay. And this was work done with my colleague Richard Pope at the University of Derby. What about the last glaciers of Greece? Here they are in the high cirques. These correspond to 10 to 12,600. And that corresponds to the classic last phase of glaciation we see across Europe, in Wales, in Scotland, so on, during the Younger Dryas, when we would have had small glaciers in the mountains of Wales, Scotland, the Alps, and also in southern Greece. So there's a uniformity of the timing of the last glaciers of Greece. Now, I say the last glaciers of Greece. Some people, Michael Stilas and others, believe there were niche glaciers on Mount Olympus, even in the Holocene. They would have been tiny, really. But by and large, the last significant glaciers of Greece ended at the beginning of the Holocene. Okay, we'll have a quick run up to Montenegro. As I mentioned, I did this when I came to Manchester. It was the original target destination. But what's interesting about this area, this is Montenegro, this is Kotor, is today it's the wettest place in Europe, has precipitation annually measured over 5,000 millimetres. The record is over 8,000 millimetres at Krikvich, which is 900 metres altitude, but the mountains are 1,800 on the coast. So we haven't got measurements there, but we're looking at 5 to 10,000 millimetres. That's right, 5 to 10,000 millimetres, huge precipitation.
Montenegro, quick, have a look at this.
Wales, look.
Oh, I missed it.
Okay.
I missed it.
So
quick.
An interesting feature of the Western
Balkans.
And what we're interested in is looking at, well, what was it like in the Pleistocene? Was it wet comparative to the rest of the Mediterranean even then? And we do see the lowest glacial deposits of the whole Mediterranean. This is a U-shaped valley with abraded bedrock steps here, going with moraines almost down to the coast. Dubrovnik's around the corner, just up the road, and anyone been to that part of the world, it's not the sort of place you expect significant glaciation, but you do. It's like Wales, apart from its limestone, largely. Okay. And you get these glacial features almost in view of the beach. This is sort of moraines you see in the mountains. That's on the coast. You can see here, Herceg Novi, Dubrovnik's up here. But interestingly, if we go inland, we then start to see interesting features. Real glaciers today. When I was doing my work in Montenegro, I was interested in the Pleistocene, Quaternary glaciations. I wasn't thinking of modern glaciers at all. And you wander around the corner mapping what you think are Pleistocene moraines, and then you see a real one. And that's easy geology because you don't have to reconstruct it. You can just go and touch it, okay, because it's there. So that's the Debelinamit Glacier in central Montenegro. It's about 2,100 meters high, a bit higher than ones on the coast. And it's quite unique. There's only one real glacier in Montenegro, but there's several real glaciers in Albania, which isn't far away. And again, they shouldn't be there, really. It shouldn't exist. It's only there because of avalanching, huge amounts of avalanching snow, high precipitation. We're not talking 5,000 to 10,000 millimeters here. It's more like 3,000 to 4,000. But what did it mean for the Pleistocene? Well, you then start to think, well, okay, we've got a glacier there now. What about during the ice ages? How big were the glaciers? And then it becomes clear that most of Montenegro, this is in this rectangle here, I showed you Oyen before, that's the extent of ice there. But if you to go to the borders of Albania, huge amounts of ice too. So Montenegro was largely covered by ice during the Pleistocene on multiple occasions, different ice ages, and the same is true of especially northern Albania. Okay, we knew that. We knew there were been glaciers in these parts of the world, but not to this extent. There's been lots of research over the years, but not really grasping how significant glaciations have been in the Balkans. Especially the timing, we've never really known, well, when were these glaciers the largest? What's the sequence of glaciation? So we've used soil profiles, uranium series dating. So this is how you visualize secondary carbonates. This is an exposure through moraine. We date the secondary carbonates, which form after the moraine was placed. We also use soils to see how the relative age of moraine sequences. And again, like Greece, these moraines, some of the biggest ones are very, very old. And that's the sort of landscape we see in central Montenegro. It's completely abraded by ice, classic ice moulding across the landscape, even the summits, and we get not erratics because they're limestone, but we get glacial boulders on the summits and so on. So it looks like northwest Scotland, apart from its limestone predominantly. Okay, and that's in central Montenegro. This is Montenegro again. This is in, I think it's late May, June. Look across the landscape, and it suddenly became apparent that, okay, we were all rushing to the cirques to map clear glacial features, but when you look beyond the cirques, you can see most of the country would have been covered by ice, and you have to put that different perspective on. You get glacial features, moraines. It's obvious once you see it, and there would have been a big ice cap, especially in the middle Pleistocene. Okay. And that takes us up the Balkans to Croatia, where the Croats, my colleague Lurka Marjanac, did her PhD, and they believe that glaciers were even bigger than in southern Balkans and central Balkans like Montenegro, Bosnia, that they would have covered the landscape. And a lot of the offshore islands, they think that glaciers even reached there. And I've been there and I've seen some glacial deposits right on the coast. It's more controversial up there because it's not as clear. Sometimes as geomorphologists, we can't see it and see the moraines and visualize it. We start to rely on geological evidence, and it gets a little bit more, is it glacial, is it not glacial, and so forth. But I think there were certainly significant ice cover in the northwest Balkans. I'll leave it at that. Some of the Croatians want ice to completely cover the former Yugoslavia, from Slovenia to Albania on the border of Montenegro, and have a mega Dinaric ice sheet. Not quite sure it's that big. Iberia, there's just a few slides here, then I'll finish in the last 10 minutes with Morocco. We're going far west, northwest now, Iberia. This is the map of the Pleistocene snow lines. Like I said before, maps onto the modern precipitation distribution. If you look at precipitation distribution for Spain and Portugal, wettest in the northwest, driest in the southeast, and the snow lines match that. So the Earth was still spinning in the ice ages. The patterns of circulation were the same. The North Atlantic was still where it was. So what it tells us is the prevailing patterns of moisture supply were the same as today. The difference is where was the polar front and the atmospheric depressions at this time. A student of mine, Tom Cowton, did some work in the Sanabria National Park several years ago, and his task was to map the extent of glaciations in this part of Spain, and what did it mean for climate. And that's Spain. Doesn't look like Spain, it looks like mid-Wales, but this is the sort of landscape we see in this part of northwest Spain. Classic U-shaped valleys, parabolic shaped valleys, misfit streams, and it looks exactly like Wales because it was exactly like Wales in the Pleistocene, completely covered by ice, not the whole of Spain, but this particular massif with a significant ice cap. And if you go down valley, you start to see the limits of where this ice used to be. And that's Tom Cowton standing on these large glacial boulders. easy to see. That's what the landscape would have looked like during the last ice age. Several kilometres long, completely submerged the mountains, and that's common to Spain. If you go to most of the mountains of Iberia, they all had big ice caps on them, extensively glaciated. Portugal too, Estrella, most of the massifs. So there was a book I contributed to opening chapter to recently on, it was called Iberia, Land of Glaciers. It's slightly misleading because there's not many there now, but the point is, the Spanish colleagues, the point was that Spain is, the surface of the landscape in Spain is largely a product, especially in the mountains, of ice. Now, we've been on a whirlwind tour of the Med. Now let's finish with Morocco, the last 10 minutes. John and I have been working in Morocco for a long time with students, taking student field trips, but I was going there for several years before working on the glacial history of the Atlas Mountains. So let's have a look at what we're dealing with. Well, first of all, you can see some of the landscape features. We've got the Sahara Desert here, the largest desert on Earth, and then you've got the Atlantic Ocean there, and then the Mediterranean Sea. And the white on the mountains on this satellite image is snow. There's no glaciers today in Morocco, but there are lots in the winter though. We'll see some evidence of permanent snow in later slides, but the landscape's clearly glaciated. You get classic features like cirques, U-shaped valleys, moraines, and so on. And that's been known for a long time. There was work in the 19th century. There was a tour of Morocco by Joseph Hooker and George Mao was a geologist on that expedition, published in 1878. And they noticed some of the classic features of the Atlas Mountains. For example, there's the article, Journal of a Tour in the Great Atlas. There was Thompson, Joseph Thompson, there's various other people through the 20th century. But there's a quote from Thompson. It was after he died from some tropical disease. I don't know what happened to him, but anyway. There is undoubted evidence of a glacial period in the later history of the mountains in the shape of moraine heaps and ice-worn boulders in their glens and valleys. And this is Morocco that he's writing about or being reported about, okay? Communicated by the president of, I think it was the Geographical Association. Okay. Toubkal, that's where I did most of the work. It's the highest mountain in North Africa, reaches 4,167, mostly volcanic rocks, basalts, andesites. John and I always have an argument about, is it a basalt, an andesite? And we've come to the conclusion after many years, they're somewhere in between. We've had a compromise agreement. Rhyolites and some granites. So it's just a stack of bad lava, effectively. And that's important because it informs the dating techniques that we use to date the surface landforms. You can apply beryllium-10 or chlorine-36. It's the same exposure dating technique I mentioned before. On limestone, we apply chlorine-36 solely because calcium is the dominant target element in limestone, and that morphs or breaks down into chlorine-36 through spallation as it's bombarded by cosmogenic rays, okay? On some rocks, if you've got enough quartz, the quartz grains, the oxygen atoms of the quartz grains break down and become beryllium-10. So we can apply beryllium-10 dating, and the physics behind beryllium-10 dating is easier than chlorine-36. The problem with andesites and basalts, of course, is they don't have much quartz in, but there is quartz, secondary quartz, and that's in the quartz veins, which is secondary to come sometime later, and we've utilised that for beryllium-10. The chlorine-36 isn't through calcium this time, it's through potassium. Potassium and calcium through cosmogenic spallation break down into chlorine-36, and there's lots of potassium in the andesites and basalts and rhyolites of these mountains. Okay, that's a map of how the ice would have looked at the largest extent of ice. So this is the sort of scale we're talking about. Several kilometres long, the largest outlet glacier is over 10 kilometres long. And most of the Atlas Mountains would have been glaciated, especially in this area. We don't know much about the rest of the Atlas. There's huge areas where there's been no studies whatsoever. So there's lots to do. What do I do? Well, effectively, wander the hills, mapping moraine features through either surface form or through the sediments, through sedimentology, subdividing it morphostratigraphically in order, one being the oldest or the lowest glaciers, the mid-valley glaciers, and then the highest, most recent glaciers, number 3. And applying these letters here is where I've taken rock samples to date with cosmogenic nuclides. Okay, so that's the general feature. It's complicated though because it's tectonically active. There's lots of things happening today, and there's evidence of significant mass movements in these mountains. So a little summary here of what the results show us. Well, beryllium 10 exposure ages from the lowest unit 1. These are the lowest moraines here, which you can still see at the surface morphologically, come out with 30 to 50,000 years. We're not confident about exactly when that is, but all I know is it's old. It's older than the last glacial maximum, remember, which is 25,000 years ago. Because in this mountain area, we've got a lot of exhumation, a lot of erosion, and there's a big scatter in these ages. But what we know, the significant thing is it predates the last glacial maximum with a snow line, which is pretty low, 2,600 meters. Remember, the mountains are over 4,000 meters. Evidence of classic GCSE sort of landforms, which they teach at school, truncated spurs, perched boulders, cirques and so on, gives us classic evidence of extensive glaciation of the high atlas, which we get our students to investigate when we go to Morocco, which we haven't done for the last 4 years, but we're going again in March. This is the mid-valley moraines, further up valley, and these date to around the last glacial maximum. And again, that's from beryllium 10. We've also got chlorine 36. Circumvalley glaciers with a snow line of around 3,000 meters. Then we go to unit 3, which is up valley again, and we get very, very clear morphological features as if the glaciers have only just left. And these date to the end of the Pleistocene Young Dryas, which is when we had the last glaciers of Wales, Scotland, and the Lake District, of course. Okay, and the snow lines here in the atlas were around 3,200 to 3,300 meters. And just to finish off the talk with Morocco, we've also got, interestingly, like in Montenegro, real snow and ice today. And that was mapped by the French in the 1930s. Del Hay produced a map in 1937, and then that was reproduced for all the topographic maps marking on this neve permanente, which is a feature which never melts. So it's a snow and ice feature which is always there at the end of the melt season in September, October, before the new snows. And that's really interesting. It's not a real glacier, but it's a perennial snow ice feature. And that informs, well, if you look at the climate of Morocco today, Marrakesh often reaches high 40s, sometimes over 50 in the summer. Even in the mountains, you're talking it's pretty hot. So in theory, these features shouldn't exist, but they do exist. And like in Montenegro and other parts of the Mediterranean, they exist because of local topoclimatic controls, avalanching snow, strong shading, sometimes covered by debris, and that these glaciers or snow patches can live in their own world, even in what is on paper a very hot climate. Okay, now in the Pleistocene, even if local topoclimate is clearly important, reducing by temperatures magnitudes for the Pleistocene, even once we go beyond these local topoclimatic settings, we still can't grow big glaciers. So in order to get big glaciers in Morocco, even in the Pleistocene, we think climate must have been wetter as well as colder than it is today. And that's really important for that map I showed you, remember, with atmospheric systems coming across the Mediterranean. And it's probably because the polar front and the production of depression systems was much further south. And this is supported by work in the Alps, where they've got speleifem records suggesting moisture supply from the south. And what we think is the bad weather we have in our country in the Holocene was characteristic several tens of degrees latitude further south through Iberia and Morocco during the Pleistocene cold stages. And further north over Britain, Scandinavia, you would have had big ice sheets and you would have had polar highs, okay, anticyclonic conditions, blocking highs. And today, when you get blocking highs in our winters over Scandinavia, you get very wet conditions in the Mediterranean. So it's analogous with that sort of synoptic situation, okay? So the work we're doing is to inform the position of the jet stream during the Pleistocene. This is the last slide. So what's still to do? Still lots to do, lots of complexity. It's problem with the Quaternary is the more you get into things, the better we can date things, we start to get more complexity and contradictions. And that's due to the resolution of time. I'm talking about separating out what happened 25,000 years ago with what happened 30 to 40,000 years ago, and the complexity of millennial scale climate change. So establishing the timing of glaciations is really important, and the significant differences between the regions. And with new techniques, we're able to do that, which we were not able to do several decades ago. Correctly interpret what it means for climate, and then what does it mean for plants and animals? A big part of why the Mediterranean is important is because during glacials of the Quaternary and the Pleistocene, the temperate flora and fauna of Northern Europe had refugia in the peninsulas of Southern Europe. And then when we had interglacials, it then migrated back again, and it has big biological and evolutionary implications for the temperate flora and fauna. And also, of course, humans came through Southern Europe, modern anatomical humans in the last glacial, and also Neanderthals in earlier glacials. We find lots of evidence on moraines of Neanderthal flints and so on. And then, of course, what do the glaciers mean for the big geomorphological features on Earth, things like the Sahara Desert? When we know it wasn't always a desert, it wasn't always dry. Even as recently as 5,000 years ago, it was much greener, okay? So lots of things that these little glaciers and the larger ice masses from the Pleistocene tell us about this fascinating part of the world, okay? And that's it, I think, and just some thanks to my collaborators. Many people have been helping me over the years working on all this. Thank you.